Introduction to Apache Avro. 1. Definition of Avro. Apache Avro is a data serialization system designed for efficient data encoding and decoding. It's a part of the Hadoop ecosystem and is widely used in data exchange for big data applications. 2. Key features. Avro is known for its rich data structures, compact, fast binary data format, and integration with a variety of programming languages. It uses JSON to define data types and protocols, and serializes data in a compact binary format. 3. Avro Data Serialization System. Avro serializes data in a binary format, which makes it extremely compact and efficient for both storage and transmission. It also supports schema evolution, allowing the schema to change without breaking existing systems. 4. Use cases. Avro is ideal for data serialization in big data processing, particularly with Apache Hadoop and Apache Spark. It's also used in remote procedure calls, RPCs, and data storage for persistent data. Avro schema and data types. 1. Avro schemas. Avro schemas are defined in JSON format and specify the structure of the Avro data. They play a critical role in serialization and deserialization processes. 2. Primitive data types. Avro supports several primitive types such as int, long, string, boolean, and float for basic data representation. 3. Complex data types. It also supports complex types like records, similar to classes in OOP, enums, arrays, maps, unions, and fixed types for representing more complex data structures. 4. Schema evolution. Avro supports schema evolution, which allows schemas to evolve over time. This feature is crucial for long-term data storage and backward and forward compatibility. Working with Avro in big data. 1. Integration with Hadoop. Avro integrates seamlessly with the Hadoop ecosystem. It is commonly used as the data serialization format for data stored in HDFS and processed with MapReduce, Spark, and other Hadoop-related technologies. 2. Data serialization and deserialization. Avro provides efficient serialization and deserialization of data. The compact binary format ensures fast processing and minimizes storage space. 3. Performance benefits. Due to its compact binary data format and efficient schema, Avro is highly performant, making it suitable for high-throughput data processing tasks. 4. Avro in data pipelines. Avro is often used in data pipelines for its efficiency in batch and streaming data processing, especially when integrating different big data tools and platforms. Introduction to RC file in Hadoop. 1. Definition of RC file. RC file, record columnar file, is a data storage format in Hadoop, designed for efficient storage and rapid data retrieval. It is a columnar storage file format optimized for data warehousing scenarios. 2. Key features. RC file's primary features include columnar storage, which reduces I/O, efficient data compression, and support for complex data types. It improves performance for read-heavy operations, particularly for analytical queries. 3. Storage format. In RC file, data is first partitioned into rows and then into columns, allowing efficient compression and fast data retrieval. This format is particularly beneficial when queries access only a subset of columns in a dataset. 4. Use cases. RC file is widely used in data warehousing solutions and for querying large datasets. It's particularly effective for Hive queries, where only specific columns of a large dataset are frequently accessed. Advantages and limitations of RC file. 1. Improved query performance. RC file format improves performance for queries that need to access only certain columns from a large dataset, as it allows selective reading of columns. 2. Data compression. RC file supports efficient data compression, which reduces storage requirements and speeds up data transfer. 3. Flexibility. It handles a variety of data formats and complex data types, making it versatile for different types of analytical queries. 4. Limitations. The main limitation of RC file is that it's not well suited for scenarios where most queries access most or all of the columns, as it may not offer significant performance advantages in such cases. Working with RC file in Hadoop ecosystem. 1. Creating RC files. RC files can be created using tools in the Hadoop ecosystem, such as Hive. When creating tables in Hive, specifying the RC file format optimizes them for columnar storage. 2. Reading from RC files. When reading data, systems like Hive can efficiently access only the necessary columns, reducing the amount of data read and processed. 3. Integrating with Hive. RC file is particularly effective when used with Hive for data warehousing queries. It is well suited for tables that are frequently queried and require fast read access. 4. Best practices. To maximize the benefits of RC file, it's important to understand the query patterns and access paths for your data. Optimize the schema and column organization based on the most common query types. Introduction to ORC file format. 1. Definition of ORC. ORC, Optimized Row Columnar, is a type of columnar storage format that is highly optimized for heavy read operations. It's part of the Apache Hive project and is used in the Hadoop ecosystem. 2. Key features. ORC offers efficient compression and encoding schemes, which reduce the size of the data. It supports complex data types and provides efficient data access through predicate pushdown and index support. 3. Storage efficiency. ORC improves storage efficiency by storing columns of data together and applying type-specific compression and encoding. It also stores metadata with the data, which allows for faster reading of specific rows/columns. 4. Use cases. ORC is commonly used in data warehousing operations within Hadoop, particularly for Hive queries. It's ideal for scenarios where large volumes of data are read and processed, and less so for write-heavy operations. Advantages and limitations of ORC file format. 1. Improved performance. ORC improves performance in reading, writing, and processing data compared to other file formats like text and sequence file, especially for large datasets. 2. Compression and encoding. It uses advanced compression and encoding techniques, which significantly reduce the data size and improve I/O efficiency. 3. Indexing and predicate pushdown. ORC supports indexing, which speeds up data retrieval. Predicate pushdown allows certain filters to be applied directly on the file, reducing the amount of data loaded. 4. Limitations. The main limitation of ORC is that it is less efficient for write-heavy operations and scenarios where data is frequently updated. It is more complex compared to other formats, which might increase the learning curve. Working with ORC in Hadoop ecosystem. 1. Creating ORC files. ORC files can be created using Hive or other Hadoop ecosystem tools. When creating tables in Hive, specifying the ORC format optimizes them for efficient storage and retrieval. 2. Reading and writing data. ORC improves read performance, especially for analytical workloads. While writing data, ORC files batch rows of data together, which enhances write performance. 3. Integration with Hive. ORC is highly integrated with Hive and is the preferred choice for storing Hive data, especially for tables that are used in analytical queries. 4. Performance tuning. To optimize the performance of ORC files, consider tuning factors like stripe size, compression format, and row group sizes based on your specific workload requirements. Introduction to Apache Parquet. 1. Definition of Parquet. Apache Parquet is an open-source, columnar storage file format optimized for use with big data processing frameworks. It is designed to bring efficient columnar storage of data compared to row-based files like CSV. 2. Key features. Parquet's key features include efficient data compression and encoding schemes, support for complex nested data structures, and compatibility with multiple data processing frameworks. 3. Columnar storage format. Parquet organizes data by column, allowing for better compression and efficient read of only the necessary data, significantly improving performance for read-heavy analytical queries. 4. Use cases. Parquet is particularly suitable for complex data processing tasks within big data ecosystems, such as querying large datasets with Apache Hive, Apache Spark, and other Hadoop-based tools. It's also used in data exchange between systems and for long-term storage of data. Advantages and limitations of Apache Parquet. 1. Improved query performance. Parquet enhances performance in read-heavy analytical queries by allowing efficient reads of specific columns without reading the entire row. 2. Efficient data compression. The columnar format allows for better data compression and reduced storage needs. Parquet files also support multiple compression codecs. 3. Schema evolution. Parquet supports schema evolution, which allows the schema of the data to change over time without affecting existing data, ensuring backward compatibility. 4. Limitations. Parquet's limitations include higher CPU usage for writing data due to its complex encoding and compression algorithms, and it's less efficient for write-heavy operations or when accessing full rows frequently. Working with Parquet in big data ecosystems. 1. Integration with data processing frameworks. Parquet integrates well with most big data processing frameworks like Apache Hadoop, Apache Spark, and Apache Hive, allowing for flexible data processing. 2. Reading and writing Parquet files. Reading from and writing to Parquet files is efficient and can be done using tools in the Hadoop ecosystem. Parquet allows for selective reads and efficient writes. 3. Optimizing Parquet for performance. Performance can be optimized by tuning parameters like block size, page size, and choosing the right compression codec based on the nature of data and query patterns. 4. Parquet and data warehousing. Parquet is highly suitable for data warehousing scenarios, especially with Hive and Spark for querying and analyzing large datasets, due to its efficient storage and fast query capabilities. Introduction to Apache Scoop. 1. Definition of Scoop. Apache Scoop is an open-source tool designed for efficiently transferring bulk data between Apache Hadoop and structured data stores such as relational databases. Scoop automates most of this process, relying on the database to describe the schema for the data to be imported. 2. Key features. Scoop provides parallel import/export, fault tolerance, incremental loading, and support for large objects, blobs, clobs. It supports various RDBMS and data warehouses, making it versatile for different data integration scenarios. 3. Data transfer process. Scoop imports data to Hadoop Distributed File System, HDFS, or Hive and exports data from Hadoop or Hive to external structured data stores. It uses MapReduce to import and export the data, which ensures efficient and fault-tolerant data transfer. 4. Use cases. Scoop is commonly used for migrating data from traditional databases to Hadoop platforms for big data processing and vice versa. It's also used for incremental loads of single tables or entire databases to keep the Hadoop data repositories in sync with external data stores. Working with Apache Scoop. 1. Importing data. Scoop can import individual tables, entire databases, or specific queries into HDFS, Hive, or Hbase. The data import process can be customized with various parameters and mapped to Hadoop's data types. 2. Exporting data. Scoop allows the export of data from Hadoop or Hive back to relational databases. This is useful for transferring process data back to an external database for use in traditional applications. 3. Incremental data load. Scoop supports incremental loads, which is the ability to import only new or updated data since the last import, optimizing the data transfer and ensuring data currency. 4. Scoop connectors. Scoop offers connectors for various RDBMS and data warehouses, enabling connections to different databases like MySQL, PostgreSQL, Oracle, SQL Server, and more. Challenges and best practices in Apache Scoop. 1. Data type mismatch. Handling mismatches between SQL data types and Hadoop's data types can be challenging. It's important to ensure that data types are correctly mapped during the import/export process. 2. Performance tuning. The performance of Scoop can be affected by network bandwidth, the database's load, and the configuration of the Hadoop cluster. Tuning parameters like the number of mappers can optimize performance. 3. Security considerations. When transferring sensitive data, it's crucial to consider security aspects, such as using secure connections and handling credentials securely. 4. Data integrity. Ensuring data integrity during the import/export process is vital. This includes verifying the completeness and accuracy of the data transferred. Introduction to Apache Flume. 1. Definition of Flume. Apache Flume is a distributed, reliable, and available system for efficiently collecting, aggregating, and moving large amounts of log data to a centralized data store. It's designed to work with Hadoop and HDFS. 2. Key features. Flume's features include its ability to handle high-throughput data streams, robustness against failure, and flexibility in sourcing, storing, and modeling data. It also supports dynamic reconfiguration without service disruption. 3. Architecture. Flume's architecture is based on streaming data flows with components like sources, channels, and sinks. Sources accept data, channels buffer it, and sinks deliver it to the destination, like HDFS, Hbase. 4. Use cases. Flume is widely used for log data collection, in scenarios like web server log aggregation, collecting data from various sources, like social media, IoT devices, and moving it into Hadoop for further analysis. Components of Apache Flume. 1. Sources. Sources are the components that receive or pull data into Flume. They can be logs, syslogs, HTTP, or even custom sources. 2. Channels. Channels act as the buffer between the sources and sinks. They temporarily store the data before it's delivered to the sinks. Types of channels include memory, JDBC, file, etc. 3. Sinks. Sinks deliver the data to the destination. The destination could be a file system, database, HDFS, or any other data store. Flume supports various types of sinks to accommodate different data stores. 4. Flume agents. A Flume agent is a JVM process that hosts the components through which data flows from an external source to the next destination. An agent can have multiple sources, channels, and sinks. Flume configuration and data flow. 1. Configuring Flume agents. Setting up a Flume agent involves configuring sources, channels, and sinks, and linking them together in a configuration file. This includes specifying types, channel selectors, and sync processors. 2. Data flow process. Data flows through Flume in a series of steps. It's ingested by sources, buffered in channels, and eventually drained out by sinks. 3. Reliability and fault tolerance. Flume ensures reliable data transmission. In case of a failure, channels will buffer the data until it can be successfully delivered to the sink, preventing data loss. 4. Scalability. Flume is designed to be scalable. Multiple Flume agents can work together, and each agent can be scaled independently to handle high data throughput. Introduction to Apache Kafka. 1. Definition of Kafka. Apache Kafka is a distributed streaming platform designed for building real-time data pipelines and streaming applications. It's capable of handling trillions of events a day. 2. Key features. Kafka's key features include high throughput, built-in partitioning, replication, and fault tolerance. It's designed for horizontal scalability and allows for real-time data processing. 3. Core components. The core components of Kafka are producers, which publish data to topics, consumers, which subscribe to topics and process data, brokers, which store data, and Kafka cluster, which manages the storage and dissemination of messages. 4. Use cases. Kafka is widely used in scenarios such as real-time analytics, log aggregation, event sourcing, and stream processing. It's popular in industries like retail, finance, and logistics for real-time data integration and processing. Architecture and data flow in Kafka. 1. Topics and partitions. In Kafka, a topic is a category or feed to which records are published. Topics are split into partitions for scalability, each partition being an ordered, immutable sequence of records. 2. Producers and consumers. Producers create and send records to topics. Consumers read records from topics. Kafka maintains a balance between producers and consumers to ensure efficient data processing. 3. Brokers and clusters. A Kafka cluster is composed of multiple brokers. Each broker is a server that stores data and serves client requests. Brokers ensure the high availability and resilience of the Kafka cluster. 4. Durability and scalability. Kafka ensures durability through replication and retention policies. It's designed to be scalable, handling large volumes of data and a high number of users and messages. Challenges and best practices in Apache Kafka. 1. Message ordering. Ensuring correct order of messages can be a challenge. It's important to design the system considering partitioning and consumer groups to maintain order where necessary. 2. Data retention policy. Managing Kafka's data retention policy effectively is crucial to balance storage and ensure data is available as long as needed. 3. Fault tolerance. Kafka's fault tolerance is achieved through replication. Properly configuring replication factors and understanding the implications is key to achieving high availability. 4. Monitoring and management. Monitoring Kafka clusters is essential for understanding their health and performance. Using tools like Apache Kafka's JMX metrics, alongside third-party monitoring tools, can provide deep insights into Kafka operations. Introduction to Apache Ambari. 1. Definition of Ambari. Apache Ambari is a management platform for provisioning, managing, and monitoring Apache Hadoop clusters. Ambari provides an easy-to-use web UI and APIs for Hadoop management, simplifying the process of keeping an Hadoop cluster up and running. 2. Key features. Key features of Ambari include cluster installation, configuration and management, centralized security setup, full cluster visibility through a user-friendly dashboard, and integration with various Hadoop components. 3. Ambari components. The main components of Ambari are Ambari Server, which manages cluster communications and state, and Ambari agents, installed on all nodes, which execute tasks and report status. 4. Use cases. Ambari is used for managing large Hadoop clusters, including tasks like cluster setup, configuration changes, monitoring cluster health, and troubleshooting issues. Ambari architecture and workflow. 1. Ambari server, the central component that communicates with Ambari agents on each node in the cluster. It maintains cluster state and provides information to the web UI. 2. Ambari agents. These agents run on all nodes in the cluster and communicate with the Ambari server. They execute management commands sent from the server and report back the status. 3. Ambari Web UI, an intuitive, easy-to-use graphical interface that allows administrators to manage and monitor their Hadoop clusters. 4. Integration with Hadoop ecosystem. Ambari integrates with various components of the Hadoop ecosystem, such as HDFS, MapReduce, Hive, Hbase, Zookeeper, etc., providing a centralized platform for managing these services. Challenges and best practices in Apache Ambari. 1. Scalability. Managing a large Hadoop cluster can be challenging. Ambari's scalability features need to be effectively utilized for optimal performance and management. 2. Security management. Configuring and maintaining security is crucial. Ambari simplifies setting up Kerberos-based security on Hadoop clusters but requires careful planning and maintenance. 3. Monitoring and alerting. Effective use of Ambari's monitoring and alerting tools is key to maintaining cluster health and proactively addressing issues. 4. Customization and extensibility. Ambari can be customized and extended to suit specific needs. This includes adding new services, metrics, and alerts as per the requirements of the Hadoop cluster. Introduction to Apache Hbase. 1. Definition of Hbase. Apache Hbase is an open-source, distributed, versioned, non-relational, NoSQL, database modeled after Google's Bigtable. It's built on top of Hadoop and HDFS, Hadoop Distributed File System, and is designed to provide quick random access to large amounts of structured data. 2. Key features. Hbase features include scalability, automatic sharding, easy data replication, strong consistency, and support for high throughput and low latency operations. 3. Hbase architecture. Hbase architecture includes components like master, for cluster coordination, region servers, to serve and manage regions, Zookeeper, for maintaining cluster configuration and synchronization, and HDFS, for data storage. 4. Use cases. Hbase is commonly used for real-time read/write access to big data, such as large-scale data analytics, user profile stores, and time series data management in various sectors like finance, telecommunications, and internet companies. Hbase data model and operations. 1. Hbase table and row. In Hbase, data is stored in tables, which are a collection of rows. Each row is identified by a unique row key. 2. Column families and columns. Data within a row is grouped into column families, which are collections of columns. Column families must be defined at table creation time. 3. Data versioning. Hbase supports versioning for data. Each cell value in a table can have multiple versions with different timestamps. 4. Basic CRUD operations. Hbase supports basic CRUD, create, read, update, delete, operations. Data can be efficiently retrieved using row keys, and tables can be scanned for broader queries. Challenges and best practices in Hbase. 1. Schema design. Proper schema design is crucial for Hbase performance. Designing efficient column families and understanding the access patterns are key. 2. Cluster sizing and configuration. Sizing the Hbase cluster correctly and configuring it properly is essential for handling the expected load and achieving optimal performance. 3. Performance tuning. Regularly tuning the cluster, like compaction settings and cache sizes, can significantly improve performance. 4. Data integrity and security. Implementing robust data backup and security measures, such as access controls and encryption, is critical in a production environment. Introduction to Apache Drill. 1. Definition of Drill. Apache Drill is an open-source, schema-free SQL query engine for Hadoop, NoSQL, and cloud storage. It's designed to perform interactive analysis on large-scale datasets stored in distributed file systems or NoSQL databases. 2. Key features. Key features of Drill include the ability to query a variety of data formats and data sources with a single query, low-latency SQL querying, and schema-free data exploration. 3. Architecture. Drill's architecture is decentralized and scalable, featuring a distributed query engine that can process data in situ without requiring data movement or transformation. It supports direct querying of files in formats like Parquet, CSV, JSON, and others. 4. Use cases. Apache Drill is used in scenarios that require interactive analysis across multiple data stores, such as querying data from HDFS, HBase, MongoDB, and cloud storage simultaneously. It's suitable for data exploration, buy/analytics, and ad hoc querying. Drill query execution and data formats. 1. SQL query execution. Drill allows users to run SQL queries on various data sources without predefined schemas. It optimizes queries and executes them across the cluster using its distributed execution engine. 2. Supported data formats. Drill supports numerous file formats like Parquet, JSON, CSV, TSV, and others. It can query these different data formats without any ETL process. 3. Schema on read. Unlike traditional databases, Drill uses a schema on read approach, which means it infers the schema of the data at query time. This allows for flexibility in querying different data structures. 4. Integration with data sources. Drill can integrate with many data sources like HDFS, HBase, MongoDB, S3, Azure Blob Storage, Google Cloud Storage, and traditional databases via JDBC. Challenges and best practices in Apache Drill. 1. Query optimization. Understanding and optimizing Drill queries for performance is crucial, especially when dealing with large and diverse datasets. 2. Handling large datasets. Proper indexing and understanding of data formats are key when querying large datasets to ensure performance efficiency. 3. Security considerations. Implementing security measures like authentication, authorization, and encryption is important to protect data access through Drill. 4. Resource management. Efficient resource management is essential in a distributed environment to ensure balanced workload distribution and optimal query execution. Introduction to Apache Phoenix. 1. Definition of Phoenix. Apache Phoenix is an open-source, SQL-based, relational database engine that enables OLTP and operational analytics for Apache Hadoop. It provides a JDBC driver to hide the complexity of Hbase's APIs. 2. Key features. Phoenix offers SQL-like querying over Hbase data, coprocessors for offloading server-side processing, secondary indexing, and tight integration with Hadoop's ecosystem. 3. Architecture. Phoenix operates as a layer over Hbase, converting SQL queries into Hbase scans, and uses Hbase as its storage engine. It leverages Hbase's capabilities for scalability and fault tolerance. 4. Use cases. Ideal for situations where fast query performance over large datasets is needed. Commonly used in applications requiring real-time analytics, operational buy, and reporting over Hbase data. Phoenix data model and querying. 1. SQL interface. Apache Phoenix provides a SQL interface for interacting with Hbase data, which makes it more accessible for users familiar with relational databases. 2. Secondary indexing. Phoenix supports secondary indexing, which improves query performance on non-primary key columns. 3. Transactions. Provides support for ACID transactions, ensuring data integrity during complex operations. 4. Performance optimization. Phoenix optimizes queries through techniques like predicate pushdown, join optimizations, and parallel processing, ensuring efficient data retrieval. Challenges and best practices in Apache Phoenix. 1. Schema design. Designing efficient Phoenix schemas that align with Hbase's storage model is crucial for performance. 2. Query optimization. Tuning Phoenix queries for performance can be challenging. Understanding the underlying Hbase model and how Phoenix executes queries helps in optimization. 3. Scalability and fault tolerance. Leveraging Hbase's scalability and fault tolerance, while understanding Phoenix's limitations, is key for large-scale deployments. 4. Integration with Hadoop ecosystem. Phoenix integrates well with the Hadoop ecosystem, including tools like Hive and Spark, but requires careful planning to ensure compatibility and performance. Introduction to Presto. 1. Definition of Presto. Presto is an open-source distributed SQL query engine designed for interactive analytic queries against data sources of all sizes ranging from gigabytes to petabytes. Originally developed by Facebook, it enables querying data where it lives, including HDFS, Cassandra, relational databases, or even proprietary data stores. 2. Key features. Presto is known for its high performance, support for a variety of data sources, scalability, and the ability to query large datasets quickly. It can handle complex queries, including joins and aggregations. 3. Architecture. Presto's architecture is based on a coordinator and worker nodes. The coordinator parses, analyzes, and plans queries, while the workers execute tasks. The architecture is designed for parallel processing of data. 4. Use cases. Presto is commonly used for interactive analysis on large datasets, data lake analytics, and as a complement to big data processing tools. It's used across various industries for real-time analytics, business intelligence, and ad hoc querying. Presto query execution and optimization. 1. SQL query execution. Presto executes standard ANSI SQL queries. It compiles queries into stages and tasks to run across the worker nodes for distributed execution. 2. Federation and data sources. One of Presto's strengths is its ability to query multiple data sources via connectors. It can access data from HDFS, S3, relational databases, NoSQL databases, and others. 3. Performance optimization. Queries can be optimized through effective use of indexes, partitioning, and choosing the right data formats. Tuning memory and CPU resources on Presto nodes is also crucial for performance. 4. Connector architecture. Presto's extensible connector architecture allows it to interface with various data sources, enabling unified querying across different data systems. Challenges and best practices in Presto. 1. Resource management. Efficiently managing resources like memory and CPU on Presto clusters is key to achieving high performance, especially in a multi-tenant environment. 2. Query planning and execution. Understanding and optimizing the query execution plan is essential for complex queries, particularly those involving large datasets and multiple joins. 3. Handling large datasets. When dealing with large datasets, it's important to use strategies like partitioning and efficient data formats, like ORC or Parquet, to optimize query performance. 4. Security and access control. Implementing proper security measures including authentication, authorization, and secure data communication is crucial in a production environment. Introduction to Apache TES. 1. Definition of TES. Apache TES is an extensible framework for building high-performance batch and interactive data processing applications, coordinated by Yarn and Apache Hadoop. TES improves the MapReduce paradigm by dramatically improving its speed, while maintaining MapReduce's ability to scale to petabytes of data. 2. Key features. Key features of TES include its ability to execute complex directed acyclic graphs, DAGs, of tasks, improved resource management, and better performance compared to MapReduce, especially for complex tasks. 3. Architecture. TES functions as a more flexible and powerful successor to MapReduce. It models data processing workloads as a DAG of tasks, with each node in the DAG representing a task or a set of tasks. 4. Use cases. TES is used primarily for improving the speed of Hadoop queries, particularly with Apache Hive and Apache Pig. It's beneficial for applications requiring multiple steps of data processing and transformations. Advantages and working of Apache TES. 1. Performance efficiency. TES enhances the speed of Hadoop data processing applications, offering significant performance benefits over traditional MapReduce, especially for complex queries and pipelines. 2. Flexibility in data processing. Its ability to define complex DAGs allows for more sophisticated and efficient processing workflows than the linear steps in MapReduce. 3. Integration with Hadoop ecosystem. TES is well integrated with other Hadoop ecosystem technologies, particularly with Apache Hive and Apache Pig, enhancing their performance and capabilities. 4. Task optimization and execution. TES optimizes task execution and resource utilization, allowing for faster data processing. It dynamically reuses resources and minimizes read/write operations to disk. Challenges and best practices in Apache TES. 1. DAG design and optimization. Designing and optimizing the DAG for specific data processing tasks can be complex and requires a good understanding of the application's data flow. 2. Resource management. Efficient resource management is crucial. Proper configuration of memory and CPU resources for TES tasks can greatly affect performance. 3. Monitoring and debugging. Monitoring TES applications for performance bottlenecks and debugging them can be challenging. Tools like Ambari can be used for monitoring TES jobs. 4. Compatibility and integration. Ensuring compatibility with various Hadoop ecosystem components and integrating TES with existing data processing pipelines may require careful planning and testing. Thanks for watching.